So hello everyone, this is lecture 27 for the solid state physics. In the last lecture we discussed about the Bloch function and we were talking about the band theory. Now moving forward in the direction, we will see this Kroning-Penney model. Okay, so it is mostly the things we are studying here will be related to the quantum mechanics. So here just we will have the idea, the upper things which we need to know, and in detail we will study in the quantum mechanics. So let's see. You have seen this type of graph. I already told you what is this. Means there are multiple atoms. Okay, so their band graphs will be look like this. Means band will be formed due to overlapping. Okay, so if there is this electron and if we wanna plot it, the potential, then we can plot this like this. Means here we consider means Kroning-Penney model we consider that this region have the same potential, this region. Okay, and this one is same and this one is same. Means here the electron will be free to move and there will be sharp decrease or increase. Okay, so we can denote this graph like this also. Okay, so in this region we will say that potential is 0, then there is sharp increase and we can denote it like this. Okay, so now if we want to write the Schrodinger equation for the electron moving, so there are two reasons. One is this reason and one is this reason. So for a particular electron, what is the equation in this region, what is the equation in this region? So let's see. If we write this as x equal to 0 and this is length a and this is length minus b, then potential can be written like this. Means it is 0 for x 0 to a and it is v naught at minus b to 0. Okay, we call it region 1, we call it region 2. Now in the region 1 we can write the Schrodinger equation as this, minus h cut square by 2m d square psi by dx square. Now potential is 0 in this region, so v psi, so here is 0 psi equal to E psi. Now we can rearrange this equation in this form, d square psi by dx square plus 2m E psi divided by h cut square equal to 0. So you definitely know what is Schrodinger equation, so you can relate with that. Means here I just put the substitute the value of v here, otherwise it's the same. For the region 2 we will put the value of potential as v naught, and first we put this 2m E divided by h cut square as alpha, so this can be written as like this. Here alpha square is 2m E by h cut square. Now for region 2, here in place of potential we will write v naught, so equation will be like this, and after rearranging we will get this equation. Okay, now we will substitute this 2m v naught minus E divided by h cut square as beta square. Okay, so this equation will be written like this. So now we have these two relations, so we don't need to go in a very depth of the solutions. So here what we did means there are multiple electron system, not a single electron system. So for solving that we can't just normally solve these Schrodinger equations, so we use the Bloch function and we assume the solution as psi x equal to ukx e to the ikx. Okay, that's why we use these trial wave functions when we have multiple electron system. And after solving these two equations and using this wave function, we get this dispersion relation. We don't need proof of this here. Okay, this is the work of quantum mechanics. Here we just need this relation only, we don't need to go in a very depth. So what will the dispersion relation we will get is this: p sine alpha a divided by alpha a plus cos alpha a equal to cos ka. So this is very important relation, and this is valid solution for all the allowed energies of electron. Means this is valid for all the energies of the band. Okay, means it is valid for all the energies. Now we will see that how this equation gave us the bands. Okay, and that is exactly the Kroning-Penney model. We will just see, just wait for a while. Here p is nothing but m v naught b a divided by h cut square. You know what are b and a, these are these b and a, and you know what is v naught, that is potential, and alpha is this 2m E divided by h cut square. So you have this equation. Now let's see what is the use of this equation. Actually in the Kroning-Penney model This equation is all you have, and it is everything you have. So let's see. Means here this LHS should satisfy the RHS, and if we plot this term and the y-axis at the y-axis, and on the x-axis we place the energy, means alpha A. Alpha is what? Alpha A is nothing but energy. So this is x-axis, the middle one, and on the x-axis we will put alpha A, and on the y-axis we will put this p sine alpha A divided by alpha A plus cos alpha A. Okay, means the left hand side of this one we put on the y-axis, and on the x-axis we will put alpha A. So alpha A denotes energy, just remember this. Now this should be equal to what? Cos Ka to satisfy the equation. And what is the maximum and minimum value of cos Ka? That are plus 1 and minus 1. Means these should be in the range of plus 1 and minus 1, only then the energy will satisfy. So we draw a line that is at plus 1, at minus 1. Now let's see, when alpha A is 0, means at this, what will be the value of this relation? When alpha A is 0, then sine 0 by 0 is 1, cos 0 is 1. It will give you p plus 1. Now p plus 1 is lie somewhere here. Now this is greater than plus 1, so this will not satisfy the relation. So this region is out of bound, means the electrons can't exist in this range, in this energy range, this one. Okay, so let's see how I plotted this graph. First, you should know that what is the plot of sin x by x. Now sin x by x can be plotted like this, and it damped down and it will tends to 0 in both sides. So I just plotted this big one is same as, it is like this. This is for sin alpha by alpha A, but here we also have this factor, that is cos alpha A. It is like simple wave like this. So when it will die out, then only this one will participate in the graph, and when it is going down, then in the last we will have this a single wave which is oscillating on the between these two, plus 1 and minus 1. So this will the plot for this equation. This is going like this, like this, like this, then it will be oscillate only in this range. Okay, same on the left hand side. Now this x-axis denotes the energy, and this should be equal to cos Ka, and cos Ka can exist plus 1 and minus 1. So only the electron, when between this range, energy is between this range, only then the electron can exist, otherwise it can't exist. Okay, so let's see, this range and this range is not allowed, means electron can't exist in this range. Then this line came between this range, plus and minus 1. So there is this energy at this point, and there is this energy at this point, and electron can exist in this energy only, because this satisfies this equation equal to cos Ka. So that's how we get our first band here. Now again, after this point it is going out of minus 1, then this range is not valid for the electron to exist. Then again when it comes here, this will be the allowed energy up to this range, so this will be our second band. Then again this will not allowed, it will allowed again from here to here, then again it will allow from here to here, then it will came inside these two lines, then all the energies are allowed, means it will become continuous after that. Okay, and same will go on the left hand side. Now see, this is the Croning-Penny model, means that as we see the bands in the band theory, same bands we are getting using this quantum rules, and we are getting bands, and we are getting some range which are forbidden energy bands and some energy bands, and this. So we can also plot, now we will see the EK graph of this curve, which is very important, and there we will study about the Brillouin zones. So first of all, you need to understand this. If potential energy is 0, then total energy will be p square by 2m, that is kinetic energy, and from here we can get the dispersion relation. P is nothing but h cut k. So E equal to h cut square k square by 2m. So using this relation we can draw the E and K curve. So it will be parabola. So let's just plot this parabola here. Okay, this is parabola. It came out from this. Here we have K on the x-axis and energy on the y-axis. Now see, this K is nothing but the angle 2 pi by lambda. So we will see K equal to 0 here. Okay, and why it is 0 here? Let me tell you why it is 0 here. So this whole equation should be equal to cos Ka, and this is on the y-axis. So at this point we see that the value of this cos Ka is plus 1. So it will be plus 1 only when K equal to 0, 2 pi, 4 pi, and K will be minus 1 when it is pi, 3 pi, 5 pi and 7 pi. That's how. So for this range K should be 0 and K should be 0. So this will lie here, K0, and for this point we will have some minimum energy, that is this energy, and the maximum energy of this band is at this is minus 1. So K equal to should be minus 1, and first is pi. So when Ka equal to pi, then K will be pi by a. So maximum energy of this first band is at pi by a, and these bands we will get on the left hand side also. So when K equal to minus pi, so K equal to minus pi by a. So we'll get the maximum energy at minus pi by a and pi by a, and minimum energy at 0. So we'll get this band. This is the band because here we have the energy. So this is the energy we'll get. Now there is some gap between this, and energy is increased because energy is increasing in this way. In this graph we have energy on this axis, in this graph we have energy on y axis. Now energy is increased but angle remains same because here it is also minus 1. So K equal to minus 1 at pi. So there is this discontinuity in the energy. So here we will show this discontinuity like this. Okay, now it will go like this at 2 pi by a because this is the maximum energy at 2 pi. K equal to 2 pi. So K will be 2 pi by a. So this is how we get. Now just repeat this video and see again and again, and then you will understand. It is very hard to understand at once. Okay, so K equal to 2 pi by a, we will get the maximum energy and minimum energy at pi by a, and there is discontinuity here because of this discontinuity. Okay, and same on the negative side we'll get this. Now this energy from this to this will give us the second band. Same for the third band, we'll get this, and it will go like this. Okay, now this region where electron can exist, this first band on the k axis minus pi by a to pi by a, we call this first brilliant zone. Okay, and from pi by a to 2 pi by a and pi by a to 2 pi by a in this range, and in the left hand side we call it as the second brilliant zone. Okay, then again going in the same direction, 2 pi by a to 3 pi by a and 2 pi by a to minus 3 pi by a, we'll get the third brilliant zone. So it is on the k axis. Okay, so that's how we define the brilliant zones. So let's end today's lecture here. Just revise this and see again and again. If you are still having any doubts, then put it in the comment section. I will try to resolve. Okay, in the next lecture we will study about the tight bonding approximation and something more. Then we will see some numericals. Then we will end this band theory. Okay, thank you everyone.